Good morning, everybody. I'm sorry about this delay. I did realize that to get a taxi in Cambridge was quite hard this week. And it took more than 40 minutes to get here. I'm at the other side of the city. Anyway, I'm Valdero Rising. I'm from Brazil. And I'm presenting today a talk estimating multiple fractional seasonal long memory parameters. It's a joint work with Artec, Palma, and Zamprogno is my student in Brazil. My presentation is what follows: the abstract introduction, the model, estimation methods, simulation results, and application. I have 2 examples and a conclusions. Well, the idea is to explore seasonal long memory process with more than one seasonal period. And what you do in this paper, you present stationarity and invertibility parameter conditions for the proposed methodology, the ordinary least square. Actually, we extended the proposed, the GP8 estimator method for this model that you are dealing with, where I'm going to present. You also establish the asymptotic properties of the methods and investigated by the accuracy by Monte Carlo experiments. Simple introduction about the Arfima process that was introduced by Huskin, 81, and Granger Joix, 80. And it has become one of the most popular two-model time series of long memory behavior. Actually, the main interest in this model is the parameter D. Oh, sorry. Yeah, here. This is the main interest in the model. It takes real number. And the usual definition of long memory is that the out-covariants are not absolutely summable. Well, here I have some reference that I have been working, and I can suggest to you if anyone is interested on it. In the Arfima process, Gilweck and Porthudak that's introduced the methods. I have on paper in Journal Time Series Analysis, Robinson, 95, Velasco, and other reference related to the estimation by comparing different kind of estimators. And all these ideas were extended recently to seasonal long memory time series. As far as I know, Porter-Hudak was the first paper that present this kind of study. And the Hasley, 94, Artec and Robinson, and I have a paper on the computational statistics data analysis, and this one that you have recently submitted. Seasonal long memory time series, of course, have similar behavior of the Arfima process. The dependence between seasonal observations decay very slowly, and the spectral density of the process becomes unbounded at seasonal frequencies. Porter-Hudak examined the US monetary aggregate series by using a simple seasonal Arfima model. Hasley introduced the flexible filter of seasonal Arfima process. He defined Arfisma, then I call it Arfima. Artec and Robinson introduced seasonal and cyclical long memory model, and among others, introduced the Garma and Aruma process. The fractional Aruma process was introduced by Giraitis and Lapos. All of these models can model long memory time series with seasonal components. Well, our model. This is a general model. XT is a time series with unknown mean and constant variance. And a multiple seasonal Arfima model can be written as follows. Here you have this filter, and dy is the fractional differencing parameter. And the other components are the AR and MA parts. Here you have a white noise process. The fractional S difference is a generalization, and then this is the binomial expression, can be written like that. And the asymptotic behavior is given like that. Well, the previous model, in the previous model, the filter of the multiple seasonal Arfima model can be also written like that. And the spectral density, where the memory parameters here, this is the seasonal, this is the frequency between minus pi and pi. And our time series with both seasonal and non-seasonal fractional differencing parameters has the spectral density with the like that, where these functions is bounded above and away from 0. Okay? And then lambda ig are the pools for g from 1 to that and I and k. Well, now I'm going to present you, to introduce you, our specific model that we are working this paper and the estimations method that we are proposing to estimate these two parameters, the vector d. What you have here, it's a two seasonal periods, S1 and S2, these two fractional seasonal memory parameters. The first assumption is the spectral density of D has to satisfy as lambda goes to 0, this condition. This is a general assumption. In your case, you have considering this process as ARMA, autoregressive. It's a particular case of this. The ARMA has a particular case of this spectral density that satisfies this condition. Well, the previous filter can be read like that, where here we have the seasonal frequency. Then doing some algebra, you arrive the values of this dij, where indicates the power or the memory of the process for each seasonal frequency and for those frequencies 0 and pi. In this case, for the frequency 0 and pi, the power is d1 plus 2 divided by 2, and it's the summation. For those frequencies, equal frequencies between 0 and the pi, the power is d1 plus d2. And for those frequencies between 0 and the pi, that they are different, that's the individual power or individual memory parameter. Our first proposition, let the process be a solution of this, like that. And we have, this is a stationary covariance ARMA process, and dy is the fractional parameter at seasonal periods sy for I is equal 1, 2. Then the stationary and invertible condition, the process is stationary and invertible if the parameter satisfies this condition, and the spectral density is given by that, where here is the spectral density of the short memory process, to say that the VT, ET. And by assuming this, the asymptotical covariance of the process is given like that, where these coefficients, this parameters has this formula, and DL is, okay. All the proofs are in the paper. Remark 1. Okay, the proposition 1. From proposition 1, you can observe that as the frequency goes to seasonal, the spectral density has this form, and for the values of alpha y, the spectral density becomes, for some values, becomes unbounded. Okay, when in any kind of any values of the frequency, okay, depends on if they are equal frequency or if they are different. And the process is stationary and has long memory if the both parameters satisfy this condition. Well, based on the spectral density of the process, I'm going to introduce you now the estimation method, but before you made three more assumptions. You consider a particular case that's S1 and S2 are multiple numbers, and you have numbers M and N that satisfy this condition and also this condition. Okay, based on the spectral density given proposition 1, you can write the log of the spectral density, and you can get one regression equation by replacing the spectral unknown spectral density by an estimate like the periodogram function, and you rewrite the equation and you get a multiple regression equation where these are the coefficients that you are interested to estimate. All this, well, here, when you write the equation, you get all these coefficients, the error, that's all. So, because we are dealing with more than one seasonal long memory parameter or fractional parameter, you have to be careful about US and also the constant, and to avoid the problems to take it as a more than, it's a big matrix like 3 by 3, and what you have done, you locally center it to avoid the constant, okay, and then rewrite the equation like that. You made some conditions or some choice about the bandwidth, and I will show you later. However, the local center is needed because, okay, the regression has different constants depending on the band of frequency, but it can be applied only satisfy this condition where it's a white noise process in the case that we are considering in our study. Our first main result is theorem 1. Under those assumptions, you give the bias, you give the variance, and that depends on this matrix 4 to 4. You avoid that constant because to get all the matrix, the variance matrix was quite big, 3 by 3. And theorem 2 give the asymptotic normal distribution for the proposed, this is a vector, okay? estimator. And here I have the simplest case, the one that Porto-Hudak applied in his work. And you have the asymptotically unbiased, the variance, that's the difference between what you are proposing, what they have done, that the variance is reduced substantially compared with them. And this is the asymptotic estimate of D. This is the simplest case. From this, you can see the variance of the estimate suggested by Porter-Hudak and also considered in Von Ray 93 is approximately 4 times multiplied by S the variance of the estimator proposed here. Well, that's usually what I do when I'm doing my work. I compare this because you can say that the method that you are investigating is a semi-parametric in the sense that you don't use whole frequency. In the case that you are simulated here, you are going to use, but in general, don't use because you have AR and the AMA components in them. Usually compare with other classical estimators, like here you have here the white noise, the Whittle estimator introduced by Fox-Itaku for the long memory process, and you consider as just for comparison purpose. Our Monte Carlo experiment, you did all the calculations carried out using Ox program, and you simulate the process by following the idea giving Roskin. And since the model that you are considering in this paper does not involve AR and the AMA coefficients, you choose the bandwidth in the regression equation to be the maximum value. Okay? Our first table, you have what I have here: sample size small, sample size 480. Usually, I don't work. Even I'm talking about long memory, I don't take too large sample size because if I can see that it works for the small sample size, I'm happy. And 480. Here I have only one seasonal period for its quarterly data. In this case, you have here a Sarfirma process with long memory errors. And then, that's the reason I wrote here S1 is equal to 1. That is not seasonal. Only this one, S2, is seasonal. You have our estimators and the Fox-Itaku, the Whittle. Well, if you look at 0.10, the bias, the mean square, and the mean value, and the mean square, the variance, and they are quite competitive with the parametrical methods. Here is in the stationary condition, because if you remember, before proposition 1, I gave the proposition 1, I gave the parameter conditions to be stationary process, and then you see the summation is 0.4. Here is 0.7. It means that at pole 0, the process is not stationary. And here is unity road. But you can see that even that situation, the process works. You get good results. The covariance, the correlation between two parameters keep the same. But of course, in the unity road process, the autocorrelation is very high. No, it's because there's no stationary process and mean reverting. Okay, the next table. Now, you are considering two seasonal periods, 4 and 12, multiple. And again, the same parameters values, 0.1, 0.3. And you can see that it works. We are quite happy with the results. The variance is quite, they are very competitive with Fox theta Q. Fox theta Q get a little, get powers. Okay, it does not work well when you have more. I think that's to the minimization that function gets lost when you involve more than one long memory parameter. And then the same here. Now, okay, you get a bigger sample size again for different as you know seasonal, and of course increase the sample size, you get better estimates. Some conclusion. Well, sorry about that. Just few conclusions, but because I want to show you an application to data, real data. Our proposed methodology performed well, even for a small sample size, and the estimators are very competitive with the parametric Fox theta Q, and the method has the advantage can be used for modeling stationary and no stationary seasonal or FEMA model. Okay, can you help me the next one, please? There, I have to open. I have here some reference, but I want to show now the application of the, because this mouse is the next. Sorry, this one. Thanks. You can leave both open. No?
Yeah.
Okay. Thanks. Well, two examples. You may think, no, because when I thought about this problem, to tell you the truth, well, it was, I could imagine, it has two seasonal periods. I asked many people that I'm close to them, that they are very familiar with of time series. And then they said to me, oh, Valderio, I have not seen any application related to more than one seasonal period, to tell the truth. Anyway, after that, I decided anyway to continue my idea, and I found out that Hudak paper and the Bonnie-Ray A3 that she gave an example. And fortunately, 2-3 months ago, when master student in Victoria, you analyze the data, is a particulate matter, and fit the perfect, the model fit perfect the data. And we are quite happy with the result. It's an application. Well, unfortunately, I could not apply our methodology in the Bonnie-Ray, the same data of Bonnie-Ray, because it's too small, 72 observations. You applied, but the results was, I could not believe. And then, but what she did, as I mentioned in the initial of this talk, she estimated by using the Hudak suggestion, and she got these two parameters by fixing these conditions. I don't do that. Okay. Unfortunately, as I told you, I could not apply our proposed methodology because it's too small sample size. Anyway, but why I brought this example here to show you that if you look at the autocovariance function, you can identify the 12 period here and also the 3 here. That's what motivation to continue on the idea of estimate more than one memory parameter, seasonal memory parameter. Here is an example That's Vitória. It's a very beautiful place. You are very welcome to visit me. It's in Brazil, nearby Rio de Janeiro. You have 731 observations. It's a daily particulate matter. And if you look at the autocorrelation function, the decay, it says seasonal 7 because weekly, it's very slowly. You also observed nearby this 0 seasonal frequency or seasonal period, it's very slowly decay of the autocorrelation. Well, my first suspicion was here I have a model with one seasonal long memory parameter and a long memory error. Okay, what you did? Using different kind of bandwidths because I was not sure about the AR or MEA coefficient present in the data. And by using different bandwidth on the regression, if you look, okay, this is too small, but if you look at here, 0.6, 0.7, 0.8, all the estimates D, smaller d, and capital D. This is not seasonal, and this one is seasonal. If you look at these results, you can suspicion that, okay, it may don't have another short-run dynamics. Well, because they are very close, they have very close results, 0.32, 0.32, 14, 11, 11, 22, then. And what you did, you filtered the series by choosing one of these. And our final model, it was a SAR firma with these two. And also because the volatility, you introduce the heteroscedastic model. Well, if you look, going back what I was telling before, this, you see that it's about the parameter here. As I suspected, probably it does not have AR or MEA coefficient if you filter the series. If you look at the AR coefficient that you have here, that's very small, it's not that large, 0.1. But you consider in the model. And then I don't have here all the residuals, the forecasting studies, because that was not the idea to show here, only one application. Thank you very much.
Okay, then let's thank again
Thank you.
Speaker.